So good evening, everyone, and welcome to this evening's lecture. My name is Kathryn Coldham, and I'll be talking all about the CMS experiment at CERN. But before I do that, let me briefly introduce myself. So I am a particle physicist and science communicator. I am originally from Dagenham in East London. I'm from a working class background, and I first worked at CERN when I was 17 years old for a work placement. After that, I studied physics at Queen Mary University of London. I then gained over 5 years' worth of experience working on the CMS detector at CERN, which included me working at Princeton University. But what is CERN? CERN is a European organisation for nuclear research. It straddles the French-Swiss border near Geneva in Switzerland. It was established in 1954, just after World War II. This was as a way of reuniting countries after the devastating impact of the war. This enabled for scientists and engineers from different countries to work together, to work towards common scientific and technological goals in particle physics. So there were originally 12 member states at CERN, and it has since grown. So there are now 23 member states with associate and observer states outside of Europe. Now, CERN is a particle physics laboratory. But what is particle physics? Particles are tiny objects that make up our entire universe. They are the very building blocks of everything around us. But just how small can they get? Let's take a person, and we can zoom in to this person's hair. So as we zoom in, we eventually reach a single strand of human hair, which is just 100 micrometers in width, or 1/10 of a millimeter. Now, we can go even smaller and find that hair is made up of cells. But let's keep going. Now, cells are made of macrofibrils. So these are bundles of smaller fibers, known as microfibrils. We can keep going even smaller, and we find that microfibrils are made of protofibrils. We keep going, zooming in more and more. We find protofibrils are made of elongated clusters of proteins, like keratin. Now, we can break keratin even further, and we find that it's made of atoms. Examples are oxygen, carbon, but let's take a carbon atom, for example. Now, the carbon atom contains electrons inside electron orbitals, but we can keep zooming even further to the center of the atom, the atomic nucleus. Now, the atomic nucleus is absolutely tiny. If you enlarge an atom to be the same size as an American football field, you would find the atomic nucleus will be the same size as a blue bottle fly at the center of that field. The nucleus is made of protons and neutrons, but let's take the proton, for example. It's 1 femtometer wide, or a millionth of a billionth of a meter. Now, protons are made of a type of subatomic particle called a quark, specifically 2 up and 1 down quarks. Now, quarks are special. They are what we call elementary particles. We can't break them down any further. They are indivisible. So how can we describe all of these elementary particles in existence? We use the Standard Model. Now, the Standard Model is a collection of different theories. It describes all of these unbreakable particles, the elementary particles, and it also describes the way in which they interact together. We have the 6 types of quark, up, down, strange charm, top, and bottom. We have the 6 types of lepton, including the electron, the flow of which gives us electricity. We also have the force carriers on the right. Now, the force carriers transport what we call fundamental forces. So, for example, we have the photon. This transports the fundamental force of electromagnetism. So this force is responsible for magnets attracting or repelling, and it also gives us chemical bonds between atoms to form molecules. We also have the W and Z bosons. These were actually discovered at CERN in 1983, and they play a role in a process called beta decay. So this makes sure that there aren't too many protons or too many neutrons inside that atomic nucleus. We also have the gluon. So this transports the strong nuclear force, and this keeps quarks inside that atomic nucleus. Is incredibly strong. But just how strong is it? So let's take this tennis ball, for example. If I drop it on the ground, can anyone tell me why did it fall to the floor? Gravity, exactly. So gravity is an example of a fundamental force, but the strong nuclear force is much, much stronger than the force of gravity. To be specific, it's 100 million times stronger. So how do we overcome such strong forces? We use, at CERN, the CERN accelerator complex. Now, the CERN accelerator complex is basically a series of different particle accelerators before our particles enter the Large Hadron Collider, the largest particle accelerator in the world. Now, us particle physicists, we use a unit to describe energy, which is called the electron volt. So here we can see the Large Hadron Collider, but where does it all start? It starts with a bottle of hydrogen at the start of this complex. Now, hydrogen atoms inside this bottle are stripped of their electrons to give us the protons that we accelerate. These protons then enter a machine called the LINAC-4, increasing its speed until it enters the proton synchrotron booster. So this accelerates it to an energy of what we call 2 giga-electronvolts. But we want to go faster. So as it passes through the proton synchrotron booster, this prepares it for the next machine, a larger machine in that complex. Now this is called the proton synchrotron. So the proton synchrotron is just over 600 meters in circumference. This increases the energy of the protons by a factor of 13 to 26 giga-electronvolts. But we want to keep going, increase the energy even further. So now there's an even bigger machine, over 10 times the size of the proton synchrotron, the super proton synchrotron. It has a circumference of about 7 kilometers and accelerates them to 450 giga-electronvolts. So this prepares it for injection into the Large Hadron Collider, the largest particle accelerator in the world. It's 27 kilometers in circumference, which is about the same size as the Circle Line of the London Underground. This accelerates the particles to nearly the speed of light, and we smash them together using detectors to tell us what has happened after these collisions have taken place. Have we produced particles that we've already seen before, but we'd like to learn more about them? Or have we produced completely new particles that we haven't seen? So that brings me to the CMS detector. The CMS detector, or Compact Muon Solenoid detector, lies 100 meters below the village of Cissy in France. It's one of two what we call general-purpose detectors, like Atlas. General purpose means that we use it to study a range of different physics phenomena. But how did it get its name? Compact, because it contains a lot of material for its size. I'll explain a bit more about that later. Muon, because it can accurately detect the muon particle, a type of elementary particle, and solenoid because it contains the largest and most powerful solenoidal magnet ever manufactured. But just how big is the Compact Muon Solenoid detector? Now, this is where I'll need your help. So we have a picture of the CMS detector. Now, can you raise your hands if you travelled here today on a red London double-decker bus? Did anyone get the bus? Okay, we've got some hands, Okay, so I want you to picture a double-decker bus in your mind. Can anyone guess, if we stack double-decker buses, one on top of the other, how many would we need to reach the same height as the CMS detector? Would anyone like to guess? So there's one guess, 8. Any other guesses? Yeah, we've got 8, we've got 5. One more guess? 10. So let's see who is the closest. So we've got 1, 2, 3, and a half. So the CMS detector is 15 meters high, or in other words, 3.5 London double-decker buses. What about the length? Any guesses for the length? Got a guess? 10. Any other guesses? Up there here, 2. So we've got 10, 2. One more guess. 5. Let's see who's the closest. So the CMS detector is actually 1.5 double-decker buses long. It's 21 meters in length. And now finally, the width. Any guesses? How many double-decker buses would we need to cover the width of the CMS detector? 1.5, 3. We've got a mixture. Got a 5. Okay, let's see. Just over one double-decker bus is 15 meters wide. So it actually contains a lot of material for these dimensions. But how heavy is the Compact Muon Solenoid detector? Can anyone tell me what this is a picture of? Did I hear the Big Ben? Nearly. This is the Elizabeth Tower. So now we're going to go inside the Elizabeth Tower. Up inside the tower, we'll go above over 300 steps before we finally reach the Big Ben, the name of the bell inside the Elizabeth Tower. But let's play a guessing game. Which is heavier, the CMS detector or the Big Ben, the bell inside the Elizabeth Tower? Can you raise your hand if you think the CMS detector is heavier than the Big Ben? Okay, so we've got most of the hands. And now can you raise your hand if you think the Big Ben is heavier? Okay, we've got a few. So let's see if you're right. The CMS detector is much heavier than the Big Ben bell. The Big Ben weighs 13.5 tons. So let's go on a quest and see if we can find something a bit closer in weight to the CMS detector. So what is this a photo of? London Eye. Okay, so we're going to play the same game. Which is heavier, the CMS detector or the London Eye? Can you raise your hand if you think the CMS detector is heavier? Okay, most of the hands. And can you raise your hand if you think the London Eye is heavier? Okay, we've got a few. So we're getting a bit closer now. The London Eye is just over 2,000 tons in weight. So if we want to find something a bit closer in weight to the CMS detector, we will have to go overseas. And we go to France. So I think you all know what this is, the Eiffel Tower. Which is heavier, the CMS detector or the Eiffel Tower? Can you raise your hands for CMS detector? Okay, got less hands. And can you raise your hands if you think the Eiffel Tower is heavier? Okay, let's see who's right. So CMS detector is still a bit heavier, but we've gotten closer now. So the Eiffel Tower is around 10,000 tons. The CMS detector is about 3,000 tons, a lot of material to be contained in those dimensions. In other words, the CMS detector weighs the same as 1,000 Big Bens. So how was such an impressive machine built? Well, when we built the Large Hadron Collider, the tunnels of its predecessor, the Large Electron-Positron Collider, were used. The Large Electron-Positron Collider was in operation just before the Large Hadron Collider. It too was 27 kilometers in circumference, so reusing the same tunnels saved time and money. But for the CMS detector, the excavation has to happen from scratch. The CMS detector is at a point called 0.5 on the LHC ring. Now, it took over 6.5 years to excavate the cavern that houses the CMS detector. The cavern is 57 meters long, 27 meters in width, and 24 meters high. Now, the detector components were actually assembled and tested above the surface of the ground and very carefully lowered down, very slowly and very carefully. Now, the CMS detector is actually divided into 15 different slices. This helped with lowering it down into the detector cavern, and it also meant that the slices were then more easily accessible if maintenance work needed to be performed. So that is how we got such a huge machine 100 meters underground. But how does it detect charged particles? Well, the CMS detector is actually made of different layers. So on the far left there, we can see where the beam pipe is. That is the point at which the protons are smashed together. The products of these collisions then spray out to the different detector layers. Each layer has a different job of detecting a different particle. But exactly how does this work? So I'll go into a bit more detail a bit later about the different layers, but now I'll give a little bit of an overview. So in red there, we can see the path that an electron would follow if it traveled through the detector. Now, the electron is an elementary particle, and it has a property of charge. It has a negative charge. This means it leaves a signal in the region that is closest to the beam pipe, called the silicon tracker. We call this hits in the tracker. The electron keeps traveling through the detector as it leaves hits and is absorbed by the next layer, the electromagnetic calorimeter. This is because it's involved in the electromagnetic interaction, which is one of the fundamental forces. Let's compare this to another particle, the photon. So the photon is neutral in charge. It doesn't leave a signal in that tracker region near the beam pipe. It too is involved in the electromagnetic interaction, so is absorbed by this electromagnetic calorimeter layer. However, you might see a difference between the two paths. The photon's path is straight, while the electron's path is curved. That's because of the photon is massless, and it travels at the speed of light. So the faster a particle travels in the detector, the higher its momentum, and the straighter its path. So let's compare these two to another type of particle. In green, we have a charged hadron, for example, a pion, which can have a positive charge. Now, this too has a curved path. It travels slower than a photon. But if we compare the directions of the paths left by the pion and the electron in red, we can see they're opposite in curvature, opposite directions. That's because they have opposite charges. The pion can be positively charged, whereas the electron can be negative. So that's why the directions are different. The pion isn't absorbed by the electromagnetic calorimeter layer. It is instead absorbed by the next layer, the hadronic calorimeter. This is responsible for absorbing hadrons. So these are a type of particles that contain quarks and gluons. But let's look at another. The neutral hadron, for example, a neutron. The neutron has a high momentum. It travels quickly in the detector, so it has a straight path. it is also a hadron, so that's why it's absorbed by the hadron calorimeter. And finally, in blue, we have the muon. So the muon has a lifetime of 2.2 microseconds before it decays. This is 2.2 millionths of a second. It travels across the entire detector, curved under a magnetic field, and is detected at the outermost layer, the muon chambers at the back. But how exactly does each layer work? So first we have the beam pipe. This is where the protons and protons are smashed together. So before I said there were two proton beams, one accelerating in a clockwise direction in the Large Hadron Collider, the other in the anti-clockwise direction, and then they're smashed together. Now, actually, those beams contain what we call bunches, which are groups of protons. There are 2,808 bunches per beam, and inside an individual bunch, there's 100 billion protons, so it's a lot of protons. There's 25 nanoseconds between one bunch and the next, so we use bunches to help make the collisions more manageable and more controlled. But I have a question for you, because we need to get an idea about how big this proton beam actually is. Can you raise your hand if you are going on a summer holiday this summer? Few. Would anyone like to tell me where they're going? You, sir, at the front?
Greece.
Pardon?
Greece.
You're going to Greece. Any others? Yep, where are you going on holiday? Hong Kong, lovely. Okay, so Greece is in Europe, and many European countries use the euro. So if we take a €1 coin, and if we were able to fire the proton beam through that €1 coin, we would see it's about the same size as Spain on a €1 coin. So it's very, very small, about 2 millimeters wide. So when these very small proton beams collide together, they produce other particles, which are sprayed out to the different detector layers and produce signals. So next we have the tracker. So this is the section of the CMS detector closest to that beam pipe where those proton beams collide. Now the tracker makes use of silicon material. Silicon's very cheap to use, and we use silicon semiconductors. So when a particle travels across the silicon, it undergoes a process called ionization on these atoms. It knocks electrons out of the atoms. These electrons go on to knock more electrons out of atoms, and we have an avalanche of electrons. So these are attracted when we apply what's called a potential difference to the silicon, where we have a positive charge and a negative charge. So the negative electrons attract towards the positive end. We read that out as a signal. We next have the electromagnetic calorimeter. Now, the word calorimeter might remind you of the word calorie. Now, we use the term calorie to describe how much energy food contains, and this is similar to particle accelerators. So calorimeters inside particle detectors are used to measure the energy of the particles that they absorbed. So here we can see the electromagnetic calorimeter, and here particles involved in the electromagnetic interaction are absorbed by this layer. But how does this happen? Well, we use lead tungstate crystals. So every time a particle collides with one of these crystals, scintillation light is emitted. The more energy the particle had, the brighter the light that is emitted. And we can read this out and look through the data. So next we have the hadronic calorimeter. Similar to the electromagnetic calorimeter, it measures the energies, but this time of hadrons. So this is what we call a sampling calorimeter. It has different layers of a brass layer and also plastic scintillator. So the particle collides with the brass layer, producing secondary particles, and that starts a chain reaction. This produces pulses of light when they collide with the plastic scintillator, and that light gets passed along optical fibers and eventually converted into data for us to look through. And now we have the solenoid magnet. This is the most powerful magnet ever manufactured. It's actually superconducting. So this means when the 18,500 amps of current passes through it, it encounters no resistance. This enables it to produce a very, very strong magnetic field at 4 Tesla. Now this is over 100,000 times stronger than the magnetic field produced by the Earth. This enables it to bend the paths of the charged particles, so we can look at the paths and measure their properties. The final layer is the muon spectrometers and the return yoke. So this is the heaviest part of the CMS detector at 12,500 tons out of the total 14,000. Now, this is used to measure the muon particle, the elementary particle, very precisely. So we use different chambers, and these can contain different gases to help detect this muon particle. We also have the return yoke, so that's responsible for keeping that really strong magnetic field inside the detector. So we rely on something called a trigger system. So every time particles are produced, that generates data that we analyze to better understand what particles have been produced in this detector. Can anyone take a guess how many DVDs contain the same amount of data as the amount of data generated by each of the 4 experiments of the Large Hadron Collider each year? Can you guess a number of DVDs? Any guesses? Couple of million? A billion? So let's see who is closest. So it's 100,000 dual-loaded DVDs each year. So some of you might not watch DVDs anymore, and you might use a movie app instead. So how many, let's say if a movie app is about 205 megabytes in size, how many movie apps would we need to be about the same size? Any guesses? Billion? So let's see. We need 4 million movie apps. So this is a huge amount of data for us to store. We can't keep all of the data that is generated by the Large Hadron Collider. This is why we use a trigger system. So this trigger system contains different algorithms, so like machine learning algorithms involved in artificial intelligence. These are trained to look through the data to identify any data that might contain signs of interest in physics that we'd want to study, and it discards the rest. So it only keeps about 10% of the data originally recorded by the Large Hadron Collider. So what are the key discoveries that have been made at CERN? So a very famous discovery was the Higgs Boson particle. So that's the newest addition to the standard model. Now, this particle was theorized in the 1960s to describe a way of how the other elementary particles get their masses. This was one of the reasons why the Large Hadron Collider was created, to search for this particle. And it took over 50 years, until 2012, until we actually discovered it. So it was the ATLAS and CMS detectors that achieved results independently of each other and confirmed its existence. But how exactly does it work? So the Higgs field is surrounding all of us across the entire universe, and particles interact with it as they travel through it. Now, the longer a particle interacts with it, the more mass it gains and slows down. So this is why, for example, the photon is massless. It travels at the speed of light and doesn't acquire any mass, whereas other heavier particles are slowed down by this field and they gain mass from the Higgs. But how exactly did we discover it in the detectors? So we can't directly detect a Higgs boson in the detector, but what we can detect are the particles that it goes on to decay into. So for example, it can decay to a pair of photons, which is the force carrier for this electromagnetic interaction. We can detect those using one of the layers in the detector, and we can measure properties such as mass, charge, momentum, which is related to how fast the particle is traveling. We then carry out what's called event reconstruction, basically working our way backwards to try to figure out what was the particle that originally produced these final particles. We call those final state particles, the ones we can detect. So we take different properties, take the final particles, and work our way backwards. Now, when the Higgs boson was theorized by Peter Higgs and his colleagues, they predicted it would have a mass of around 125 giga-electronvolts. So that's 125 times more than the mass of a proton. So here is one of the famous plots that was announced in its discovery. Can you raise your hand if it's a bit confusing, that plot? Yeah, let's make it simpler. So along the x-axis, we have mass, and the y, the number of events, the number of times we think we've seen a Higgs boson in the data. Now, we plot the mass, and there was a fluctuation in the data at 125 giga-electronvolts. We therefore predicted that, yes, we have observed the Higgs boson in the detector, and this was observed by ATLAS and CMS, both collaborations, in the same year, so that validated the results. But what have we discovered since the Higgs? It's been over 12 years since the discovery of the Higgs boson. Well, since then, we've conducted different precision measurements. So we've been able to measure the Higgs mass even more precisely. We've also observed different combinations of particles in the detector. So for example, even last year, we announced an observation of a process called TWZ, which is a top quark produced next to a W boson produced next to a Z boson. We've also had other particles produced alongside each other, for example, 4 top quarks, and there was also the tetraquark discovered at CERN. Now, this is a particle that contains 5 quarks, and at CMS, we observed a tetraquark that contains 5 charm quarks. So we've observed many different types of particle, many different combinations of particle since the discovery of the Higgs boson. But how is it all achieved? Now, this is achieved by people. So there are nearly 6,000 people that are a member of the CMS collaboration. Now, this is a mixture of different people, from physicists, engineers, technicians. We also have students and administrative support staff. Now, this is a truly global endeavour. There are nearly 250 institutes that are a member of the CMS collaboration from nearly 60 different countries, all collaborating and working together. Some of those are based at CERN, near Geneva in Switzerland, whereas others are working for different universities and research organisations around the world. But what is in store for the future? So we've come a long way with the standard model, but it is far from complete. For example, you may remember with my tennis ball, I talked about the force of gravity. We haven't observed a particle that transports the force of gravity. For example, the graviton is one that has been proposed, but we haven't observed it in the detector. So there are searches ongoing to see if we can find a particle that can transport the force of gravity. Additionally, the standard model only accounts for 5% of the universe. The remaining 95% is dark matter and dark energy. Now, dark matter is important because if we have spiral galaxies in the universe, if we study the rotation of those galaxies, the outermost regions spin faster compared to the amount of matter that it contains. So therefore, there must be some extra matter to describe this behaviour, and this is in the form of dark matter. So we haven't found a particle that can explain this, There are some proposals, for example, WIMPs, weakly interacting massive particles, but we are still searching for particles to transport dark matter, dark energy. So the LHC will be improved and upgraded as part of the high luminosity LHC project. So the way the LHC works is since 2008, when it started operation, it goes through periods of where it's running, it's taking data, and there have been 3 run periods. So we're currently in run 3. In between those, there are what we call long shutdowns. So this is when the detector is completely shut down and we perform maintenance work and upgrade work. So this current run period is expected to last till 2025, and then there will be the high luminosity LHC installation. This is to improve, to increase the energy at which we collide the particles together, so that the next run period, run 4, from 2029, we can collide them at 14 tera electron volts. So how does this affect the CMS detector? There are various upgrades that will take place. For example, the trigger system that looks through the data and tells us what's interesting and what's not and discards the rest, that will need to be updated, because there will be an increased rate at which data is produced. We'll also completely replace the calorimeter regions, the electromagnetic calorimeter and hadronic calorimeter, with a completely new calorimeter, the high granularity calorimeter. We'll also upgrade the electronics in the muon systems. We'll have a new tracker system, because when we collide particles at higher energy, that means the radiation levels are higher. Now, this is completely safe for people. It's 100 meters below the ground, but this does mean that the electronics and components used need to be replacing to be able to survive that high radiation environment. There will also be a completely new detector, the minimum ionizing particles timing detector, to detect when particles arrive more precisely. But what happens after 2040? Now, there are different proposals, one of which is a future circular collider. Now, you might remember I was talking about the CERN accelerator complex as the protons speed up until they enter the Large Hadron Collider. There has been a proposal to add on an extra machine onto the end of that complex called the Future Circular Collider, or the FCC for short. Now, the LHC is 27 kilometers in circumference, the largest particle accelerator in the world. The FCC is proposed to be 100 kilometers in circumference and will reach collision energies of 100 tera electron volts. So why do we need bigger machines? Well, by having bigger machines, we can smash particles together at higher energies, and this can unlock areas of physics that we haven't been able to study using the Large Hadron Collider. Another alternative is the Muon Collider. Now, when a charged particle is accelerated in a ring, it emits what we call synchrotron radiation. It loses energy because of this. Now, with the muon, if we compare it to an electron, the muon is over 200 times heavier. Because it is heavier, it loses 2 billion times less synchrotron radiation. So that's what motivates us to build in a muon collider. Additionally, a muon is an elementary particle, so we might be able to reach higher collision energies. For example, a 10 tera electron volt muon collider might reach the same energies as a 100 tera electron volt proton collider. So there are different proposals of what comes after the LHC. So how can you get involved? So there are many different jobs at CERN. Some employed by CERN, others you could be employed by a university or research organisation. These range from work experience for students to internships to physicist, engineering jobs, as well as jobs in other fields like science communication or international relations. So many different jobs. You can actually visit CMS in real life. So the CMS detector is 100 meters below the village of Cissy in France, and you can visit it in real life. So you'll go, and then you'll go to 87 meters below the ground, and you'll see the detector. When you visit, you can also see the control room. So in this, we have people monitoring the CMS detector. They perform shifts, 8 hours each, to make sure that there's someone watching the CMS detector day and night to make sure it's operating as we want it to. You can actually analyse CMS data. So about a month and a half ago, open data was released. So this is data that the public are allowed to look at. You can look through it. You can use different coding languages to try to understand what the data is saying, like C++ or Python, and you might be able to discover your very own Higgs boson. So there are lots of physics papers produced, but there are also physics briefings. So these are aimed at a public audience about what new particles have been discovered, any combination of particles, and new advancements made by the CMS collaboration. And there is also a blog called the Cylindrical Onion, because the CMS detector is like a cylindrical onion. It has many different layers. CMS is also on social media too: Twitter, Facebook, Instagram, YouTube, and LinkedIn, so be sure to follow the accounts for updates. So that nearly wraps up my lecture, but I'd like to give a very important message. So I'd like to dedicate this lecture to my friend, Natasha Domenica Hare. So Natasha, we were best friends during our days at Queen Mary, and we both studied physics together during our undergraduate days. She was very passionate about physics. She was studying for a PhD at Queen Mary, and she really loved outreach too. She gave lots of different talks in different schools. And yes, she was very enthusiastic, and she was a brilliant friend. She very sadly passed away last year. So I'd like to take this opportunity to please encourage you to donate whatever you can to Cancer Research UK by following that link, where Cancer Research UK is the largest independent cancer research charity in the world. So that rounds up my lecture. Thank you very much.